Hello everybody, welcome back to this course on combustion in air breathing aero engines. Now last class you have seen that you have seen details of chemical kinetics from a generalized viewpoint. We introduced the concepts of a generalized reaction, then we introduced law of mass action, and then we introduced the reaction rate constant or the reaction rate coefficient, and the concepts of activation energies, etc. And then we discussed how we can describe explosion, that is fast reactions which leads to rapid release of energy due to the chain branching steps. Okay. Chain branching, which is an essential reaction that is involving the chain carriers. So this we have seen, but that was, as you have seen, that was basically, and of course we have also looked into the different theories of reaction rates, namely the collision rate theory and the transition state theory. But as you have seen that this was done for generalized reaction, and we did not discuss specific reactions that is specific to combustion in air breathing engines as such. But that so what we will do in this class is that we will use that generalized framework that was introduced in last class, and here in this class we will look into specific reactions that are of interest in an actual practical combustor. Okay. So that is what we will do here. So what we will do is that as you see here, we will talk about the reactions involving hydrogen, carbon monoxide, methane, and not only because these are important fuels, but the idea is that if you understand the reaction mechanism of these, the reaction mechanisms through which the hydrogen combusts or hydrogen oxidizes in presence of oxidizer, how carbon monoxide oxidizes, how methane oxidizes, these reaction mechanism form integral parts of reaction mechanisms of complex fuels that are used in actual air breathing engines, right. So that is the idea, and then we will look into pollutant chemistry. Of course when you design a combustor, you have to ensure two things, basically, that number one, it should be producing the required amount of power, that it should burn the fuel air mixture that you are sending in, okay, and it should burn cleanly. It should not produce too much of NOx and too much of soot. So soot and NOx are two major pollutants that are a result of hydrocarbon combustion, and we will try to understand the reaction mechanisms of the formation of those pollutants, and then we will go into mechanism development. Okay. So mechanism development and also mechanism reduction, that is we will often see that the reaction mechanisms that are of interest, that is for example involving combustion of larger hydrocarbons, those often involve too many species and too many reactions. Okay. And as a result of that, it often becomes prohibitively expensive for their use in a given CFD code. Okay. Suppose you want to do the computational fluid dynamics simulation of an actual combustor. Okay. So then you would want these realistic mechanisms, but then these realistic mechanisms are so large that you cannot use it for a practical simulation. So what you need to do is that you need to reduce its size, make them compact, so the number of species and number of reactions used are tractable, the numbers are less, so that we can do the simulation with required amount of computational power. And of course it compromises on the accuracy, but we have to ensure that we desire some kind of properties and desire some kind of accuracies, so that those are compromises at a minimum level. Okay. So we need to understand mechanisms, the oxidation mechanism of fuels, basically without that we have no idea about how the products are being formed and as a result of which even which products will be formed and what we can do, how we can engineer so that we can make sure certain properties are, certain desired properties are maintained inside the combustor. For example, you can have always a flame stabilized inside the combustor, whereas certain undesired properties like pollutants and emissions, those are mitigated. Okay. So, first the thing is that before we go into the details of the oxidation mechanisms, what we will study here is that we will go into the practical fuels, just to as a reminder of what the practical fuels are, what those names are, what their nomenclature is, and how their structures look like. Now, first of all, you will see that in most of these practical fuels, this becomes the CH2, and of course, this portion of the CH2 forms an integral part of all practical fuels. And this is of interest because if we just consider this just the reaction of this CH2 with this hypothetical reaction of this CH2 with oxygen, this oxidation, what we will see is that the heat release is huge, 156 kilocalorie per mole, and this is kind of you do not encounter this kind of very large heat release in any other other reactions in chemistry. So, this is this large heat release in a small molecule, and as a result small mass and small volume, that is very high energy density. Once again, this very high energy density of the hydrocarbon fuels is what makes them very attractive for air breathing aerospace propulsion. Okay. So, now let us look into some of the typical fuels. You see that these are the typical fuels. For example, this can be alkanes, CmH2m plus 2, where m can be anything from 1 to many large number. Of course, this is, as you see, this is N-butane, this is a normal butane, and straight chain alkanes. You can have this trimethyl pentane, where methyl group can be attached to this second carbon atom. These are the radicals, 1 butyl radical, 2 butyl radical, which will encounter in different oxidation mechanisms, but not all alkanes are straight chain alkanes. You can have cycloalkanes. Okay. And for example, this is a cyclopropane, this is the cyclic structure which gives that name, is the cyclopropane, and you can have the cyclohexane, right. But remember that this is not, this is different, this is not benzene, because in benzene you have this double bonds at alternate places, right. So, but the properties of course cyclohexane and benzene are very different. Okay. And then you can have alkenes, which is represented by this double bond here, CmH2m, and then you can have 2-butene alkynes essentially involving triple bonds, propyne, this kind of things, and of course you can have aromatics, for which we are talking about, that is benzene, which gives this the double bonds at alternate locations, and this gives cyclic structures. Now, we will soon realize that aromatics, even if you start with simple molecules like alkanes, like this one, N-butane, under different because of the complexity of the reactions, different species will be formed, different species, different radicals, even in some cases the aromatics will be formed. And when we will go into soot chemistry, formation of soot, we will see that these aromatics play a very important role in the soot chemistry. Okay. And then of course, this as we just said, that these polyaromatic hydrocarbons, or PAH, which is in its condensed form is called naphthalene, in its uncondensed form is essentially a biphenyl molecule, and this forms important are very important soot precursors. That is, before soot forms, these things form, and these forms an integral part of the soot reaction mechanisms. And of course, we can have alcohols, as you know that there is a lot of interest in making methanol, butanol, these things, ethanol work in engines, car engines, and they can also emerge as useful fuels for future aircrafts. So, but they have, because of the large water content, they have lower heat content, but they also produce lower soot. So, it is beneficial, they are less polluting. Now, The course is, as you know, as we know, it is combustion in air breathing aero engines. Now, what is the most important fuel used in aero engines? For example, in an aviation gas turbine engine, what does it use? It uses some variants of kerosene, which is called aviation jet fuel or Jet A. Jet A, Jet A1, known as slightly variation in composition, and these names come from their use in different countries. So, what is Jet A? Here you can see the composition of Jet A. It is as in contrary to what we just discussed of normal alkanes, cycloalkanes, etc. It is not a single fuel. It is essentially a combination of this different kind of alkanes, aromatics, etc. So, as you see here, these Jet A contains about 19% of aromatics, that is benzene, phenol, etc., mainly benzene type of species. But the rest is like isoparaffins. Paraffins are but nothing but alkanes. Iso is a position of the methyl radical where it is attached to a carbon atom. Normal paraffins, normal alkanes, cycloalkanes, dicycloparaffin, tricycloparaffin. So, the rest 81% is nothing but alkanes. Okay. Now, of course, when you do a fundamental study or a CFD simulation, it is very difficult to use all these kinds of different species even at the starting point. So, what we do is that we use something like a surrogate fuel, which is a representative fuel which represents the properties of Jet A very well. So, how do you get such a representative fuel? So, you find out this what are the composition of Jet A, and you come up with an average formula of Jet A, which is given by C. This is a C11.37 H21.87, and the hydrogen to carbon ratio is 1.92. As you see, the hydrogen content is 1.39% by mass, molecular weight is about 158.6 gram per mole, and its density is less than water at 0.804 gram per milliliter. Okay. And as we said that depending on these things, N-dodecane, that is C12H24, becomes a good choice for the surrogate fuel for Jet A. This is typically the composition of fuels that is used in aviation gas turbines. Okay. Now, why are we talking about this? We are talking about this for example, we will just discuss something here. Now, how do you characterize these fuel properties? Now, one important property of fuels is basically what is its ignition delay. What is ignition delay? Now, suppose you take the fuel and air you take the fuel air mixture in a container, in a closed container which is adiabatic, okay, and of course, the fuel and air are mixed at a given phi, and this container is maintained at a temperature T, and it contains fuel plus air. Now, of course, as you know that our general common sense or intuition suggests that if this mixed fuel and air, which is perfectly mixed, it's homogeneously mixed, and if it is in a mixed state, it is in a perfectly mixed state, and now if the temperature and the pressure is sufficiently high, you know that for reactions to happen the temperature and pressure needs to be sufficiently high, you know this thing will ignite. Okay. So, ignition means its temperature will rise. So, if we plot the temperature versus time, you will see that if this is my initial temperature, say this was my initial temperature Ti and Pi, then the temperature will rapidly rise after some time. Now, we can say that the ignition delay time is the time, basically the time it takes for the mixture to rise at up to a specific temperature, which can be like say you define as like 400 Kelvin difference from the initial temperature to the which we define as the ignition temperature. So, ignition delay is nothing but this time. Okay. So, this is one very important property of that we need to characterize for fuels. All right. Now, why are we talking about this? we are talking about this because you will see that even if the temperature and pressure is sufficiently high, suppose the initial temperature of you are taking say this jet fuel or its surrogate, suppose you are taking N dodecane, and the initial temperature and pressure is about, the initial temperature is about 800 Kelvin. Okay. Now we are considering say dodecane and its Ti is equal to say 800 Kelvin and its initial pressure is say 20 atmosphere. It is a relevant temperature for gas turbine engine, right. So, how long does the fuel air mixture take to ignite? Of course, this is dodecane plus air. So, then we can, what we can do is that once again we can do this kind of an experiment and we can find out the, how much the temperature rises. This can be done in a shock tube or a homogeneous reactor or in a any kind of this kind of flow reactors. Okay. So, and we find out the ignition delay time, and then we can vary the initial time, initial temperature, and we can find out a correlation by which as a function of the initial temperature, that is how much does the ignition delay time is as you change the temperature. And when you get this, you can form a correlation like this, that your ignition delay time can depend on pressure, it can depend on the mass mole fraction of oxygen, it can depend on the carbon number, etc. Okay. So, this is an alkane ignition delay. I will not go into the details of this, but one can find different kinds of correlation. Okay. And the data will actually look something like this. Okay. This is T ignition delay in milliseconds and this is 1000 divided by temperature. So, what we have done is that we have done this experiment where we took the fuel air mixture in a perfectly mixed state and then we varied the initial temperature. Okay. Now, as we vary the initial temperature, the ignition delay time changes. Okay. For example, here you see the initial state of the mixture was phi equal 1.0 and pressure is equal to 20 atmosphere. And you see that if we start, what this plot tells is that if we start at a say this value of 1, which is means 1000 by T is equal to 1, which means T is equal to 1000 Kelvin. So, the ignition delay time at this point is about 1 milliseconds. Okay. If we increase temperature, all right, that is if we increase temperatures to about 1000 if it was 2000 Kelvin, then it will have shifted here. So, when we increase, if T increases in this direction. So, as you see T, when T increases the ignition delay actually goes down, but here is something complicated happening. It is actually the ignition delay is instead of as you decrease the temperature now here it actually goes down, which is very counterintuitive, but we will go into this later. But what I want to say is that even at a temperature as high as 1000 Kelvin, or if it is less than 1000 Kelvin, if it is at say this value when 1000 by T is equal to 1.2, the ignition delay time is a finite number of about 1 millisecond. Okay. So, this is a typical number of ignition delay time of 1 milliseconds. All right. Now, why are we discussing all these things? The reason is that this ignition delay time of 1 millisecond is the time required for this fuel air mixture to ignite. Okay. So, you have to design a combustor in which your flow residence time scales must be greater than 1 millisecond. Okay. So, that is why these things are important, and then if you want to predict the behavior, the actual behavior of combustion happening inside a practical combustor, you have to capture this ignition delay time properly. And this ignition delay time, this proper capturing of the ignition delay time can be only done when you have a detailed reaction mechanism. When you from a given fuel you can break it up, when the fuel breaks up and it becomes small and small molecules, it becomes the product through a series of steps. These sort of finite ignition delay times cannot be predicted by global chemistry. So, to predict these kinds of very specific and very important properties like the ignition delay time accurately, you need you need detailed chemistry. Now, under what circumstances do you have to bother about this kind of ignition delay time in terms of a practical engine? Let us consider two cases, like say two combustor. One is say a gas turbine combustor. Okay. Here say you have solars etc., and flow coming in. Say the flow velocity inside is about, the average velocity is 100 meters per second. Okay. This is say how much, much less than 1 meter, say 0.5 meter length of the combustor. This is the gas turbine engine combustor. Okay. So, here the fuel air mixture is coming at a velocity of 100 meters per second, and the length of the combustor is 0.5 meter. Okay. Now, of course, there are many complexities, as you know, that it is basically in a gas turbine engine we inject the fuel in liquid form. So, it is injected in a spray form. So, the spray must atomize, it must the spray must break up, it must atomize, it must evaporate, mix and then combust, but let us not go into these things. Okay. So, just by these two information, that its average velocity is about 100 meters per second and the length of the gas turbine combustor is 0.5 meter, we can find out the tau residence time scale tau s as the length of the combustor divided by the flow velocity. So, then it gives as is basically half a meter times 100 meters per second. So, this gives you essentially a time of 1 by 200 seconds, which is nothing but 1000 by 200 milliseconds. Okay. So, it is about 5 milliseconds. This is 1 meter, this was meter per second. Yes. So, the time scale available is about 5 milliseconds, whereas you see it is not hugely different from what the ignition delay time of Jet A was. Okay. So, you have to ensure that the fuel, whereas ignition delay time as we discussed is a time for the homogeneous mixture to go from initial state of Ti to the product state, okay, to ignition, to at least ignition to a sufficient level. So, you have to design combustors in such a way so that you can have complete combustion and less pollutant emission. Okay. Now, if you are doing a CFD calculation of this gas turbine combustor, then it clearly says that to resolve the ignition delay time of about 1 milliseconds, you need to put in all the detailed reaction mechanisms by which the fuel will go from the large fuel molecule of dodecane to, it will break down into smaller and smaller pieces of fuel. It will become methane, ethylene, ethane, propane, butane, etc., and all these things, and then it will oxidize through different reaction mechanisms. There will be chain branching, there will be chain initiation mechanisms, there will be chain carrying mechanisms, there will be chain branching reactions, and then it will go to complete combustion. So, to understand this thing and to resolve these kinds of ignition delay, to resolve this, to arrive at this 1 millisecond, you need detailed chemistry. Okay. By detailed chemistry, what I mean is that you need all these detailed steps and detailed this numerous species by which this can be predicted. This situation is even more complex in a scramjet combustor. Okay. Let us consider a scramjet combustor where the flow velocity is about 1000 meters per second, and this is about say 1 meter. Okay. Now, here your temperature is say about 800 Kelvin and your pressure is about 1 atmosphere or 0.5 atmosphere, something like that. So, once again we can estimate the residence time scales, which is nothing but the length by the average velocity, and that comes out to be like 1 by 1000 seconds is equal to 1 millisecond. Okay. So, in this scramjet combustor, you see the residence time is equal to the ignition delay time. Of course, this is at high larger pressure, but still this is 1 millisecond, right. So, when you are, suppose you are doing a simulation of a scramjet combustor for design purposes or for other validation purposes of your scramjet combustor code. So, the thing is that you cannot design it properly, you cannot arrive at proper validation until and unless you have enough reactions in your calculation which can predict this ignition delay time of 1 milliseconds. And then after you do that, you have to do engineering, and that is why CFD calculations are important. You have to do engineering so that you can have a stable combustion. If you do not do anything, you see that you cannot have stable combustion, because this fuel and air packet is reaching here at 1000 meters per second. So, by the time ignition starts, it will already reach the end of the combustor, right. In 1 milliseconds it will travel this distance, and that is the time it takes for it to ignite. So, it will go out in the out of the combustor, and then it will get mixed with the outside air, and there will be no combustion, and then there will be no thrust and no power generation. So, to properly design the scramjet combustor, you see you really need to have detailed reaction mechanisms. Okay. So, that is the importance of reaction mechanisms, which is clearly understood from a comparison of a residence time and the ignition delay time. Of course, here we compared very simplified quantities, it is just a back of the envelope calculation. Your residence time scale is a very crude measure here, and so is the ignition delay time scale, because the process is much more complex. The most important thing is that it is not in a homogeneous state. Even though it can start from a homogeneous state, the combustion does not happen in a homogeneous state. You will see that flames differ from this kind of things, because in flames you will have diffusion, you have heat conduction, and you will have viscous effects. So, this thing is in an actual engine, things are more complex. Nevertheless, this gives a clear idea about that the competition between your flow time scales and the ignition delay time scales. Okay. And to resolve this thing properly, your CFD codes must have some amount of details of the reaction mechanism. Now, when we mean some amount of details, what are we actually meaning? What details are we putting in? Okay. What are the steps that is required to predict this kinds of ignition delay? Why 1 millisecond time is required? Why do you see this dip in the ignition delay behavior, etc. So, to study those, we will go into the details of the reaction mechanisms.